effect of X more than 2 periods ago has no effect on my behavior. I remember X today, I remember X a period ago, and then I remember X 2 periods ago. But after that, the effect of X has no effect, right? So this is just a more concrete model than that T plus Q plus 1, blah, blah, blah. Okay, so X is constant, it's equal to C in all time periods, up until times T. And then we're going to increase it by 1 unit. So C is some amount that we're spending. Then we're going to increase C by 1 unit. But then it reverts back to C at T plus 1. That's confusing. So what happens? Right before the increase, remember advertising was some constant, right? That hasn't changed. We're going to increase advertising by 1 unit in the current period, which is this period here, the coefficient of beta 0. But a period ago, it was still C, and 2 periods ago, it was still C. So this is the only increase that occurs. So beta 0, Y is going to increase by beta 0. But remember, advertising reverts back to C. So now in one period later, in period T plus 1, advertising reverts to C. Last period is when we increased it, right? And then this is before the increase. So here's this bubble that's kind of working its way through. Started here, then it's going to go here, and 1 period later it'll be, all right, so here's the bubble. Starts here. This was last period, reverted back to C, and in period T plus 2, then it's this effect here. So, what is this? This is the effect of the increase in advertising from 2 periods ago. Beta 1 here is the effect of advertising from 1 period ago. And beta 0 is the effect of the increase in advertising in that current period. Now this bubble is going to work its way through. So remember, we have a 2-period model, so T plus 2 plus 1, we're going back to where we started. So this looks just like this prior to the increase. We're back to where we were before. So here we have this bubble that kind of works its way through. Increased advertising, 1 period, and then next year we'll see the effect of that increasing advertising from a period ago, and the year after that we're going to see the effect of the advertising from 2 periods ago. But everything reverts back to its normal level. Does that help? A little bit? Maybe? If I say so? Okay, then it reverts back. So we're kind of literally looking for that bubble, right? It's going to work its way through, and then essentially what we're saying in 2 periods we're back to where we were. So this is a lot like that picture there. There's going to be some effect. Then that effect's going to diminish, so it'll be here from a period ago, and then it'll be 2 periods ago, and then it'll just die out completely.
So on that graph that you just drew, where's C? Where do you start?
So we're saying that, so here's sales, and here's period T. Before T, which is T minus 1, sales, advertising was constant.
Okay.
But then in period T, we increased advertising in just that period. But in period T plus 1, advertising went back to C. So we only increased advertising in that one period. Then we went back. So in period T+1, advertising is back to C. But now we're still going to have a lagged effect of that increase in advertising, and that's going to be measured by beta 1. 2 periods later, we're going to have a lagged effect of that increase in advertising, and it's measured by beta 2.
So C is the initial effect of advertising.
C is the initial expenditure in advertising.
Okay.
C+1 is that increase.
Okay.
And, okay, here's a permanent increase. So we're going to do the same thing, except we're going to say, we're going to increase advertising by, I'm just going to skip this. This is more confusing than it needs to be. All right. This is going to be a permanent increase. So prior to the increase, we're spending some amount on advertising, some constant amount. Then we're going to increase it by 1 unit. But we're going to keep it, we're going to not keep it, we're going to keep, this is going to be the new level of spending. This is going to be the new permanent level of spending. We're always going to spend C+1. So now we're looking at an increase in advertising, but a permanent increase. So we increased advertising. Beta 0 measures the effect of the immediate increase in advertising. Remember, beta 1 is the lagged effect, but we didn't change it a period ago, so this is still C. And we hadn't changed it 2 periods ago, so this is still C. So the immediate effect is here. This beta 1 and 2 represent the effect of the old levels of advertising 1 and 2 periods prior. And that's a mouthful. All right, let's go 1 period later. So beta 0, again, is that in period T+1. This is the last period. This is this one. And 2 periods ago, we still had an increase, so it's still C. And then 2 periods later, then we've got C+1 as the permanent. And that's, in essence, where it stays. It's always going to be C+1 until they change it again. So what are we looking at? Are we looking at a one-time increase in advertising, or are we looking at a one-time, or are we looking at a permanent increase in advertising expenditures? So this is how we measure them. We're going to actually have to measure these. Okay, long-run effect, yeah, beta 0.
What do you mean expenditures and advertising?
Let's say that's C, what C is. So in what we're saying is that our X is our advertising. And let's treat C as some dollar amount. We've spent C for the last 10 years, we've always spent C. We're going to increase C from by 1 unit, whatever that is, $100,000. So think of it like this. So now let's look at advertising. So this is advertising. This is over time. Here's time T, T minus 1, T plus 1. So we've been spending C dollars for all the years prior to period T. In period T, if it's a one-time increase, we're going to go here. But then we're going to return to that constant level. So this is a once-in-a-lifetime or one-time event. Then we want to trace this increase in advertising on the effect of sales. And this is kind of that one bubble that goes through, and how do we measure it? Versus a permanent increase. That make sense? Okay. So now let's go to a permanent increase. We've been spending C dollars, and this was C plus 1. Whatever that is. We've been spending C dollars for the last however many years. we're gonna increase advertising expenditures because we think we need to. And now that's gonna be a permanent increase, so we're always gonna spend C plus $1 instead of just C, and we're not gonna go back. So this is this case here. The one-time increase was the previous case. I want to make sure that things recording.
You can see the board.
Can't see the board.
Let's see
No,
the-
Can't see the board. Sorry.
What happened?
I was hoping that the video camera could see the board.
Oh, the
Not
board.
just
the
Gotcha,
slide.
gotcha.
Yeah, sorry. So the last graph you drew showed the sales lines. We haven't yet talked about how this translates into sales.
Yeah,
Or we did.
through these. So this is what we're looking at here.
Oh.
And it's going through the coefficients here.
Okay.
Yeah, this is why nobody does this stuff. It's complicated. Let's see, Granger causality. We'll get back to Granger causality. We did Granger causality, didn't we? 580? No?
No, not like, no.
Granger causality, well, let's cover it now. It was developed by a guy named Granger. And it's really an old method, and it's really kind of a tried and true, kind of classic method. And it basically says, can we, we always hear in statistics that you can't prove causality, you can only prove correlation. This is one measure of causality. Specifically, they call it Granger causality. And he won the Nobel Prize for this. It's, as nasty as it looks, it's really simple. So here's this equation. And essentially what you have is, this just seems higher for some reason. Either that or I got it shorter. Essentially what you have is y as a function of lag values of itself and lag values of x. So think of this again in terms of sales and advertising. So y sales as a function of past sales and a function of present and past advertising. So, if sales are doing nothing but following a trend. So this kind of goes back to what we talked about earlier. If sales were simply following this trend, if this is what sales look like, what's the best predictor of sales? Previous sales, exactly. So the best predictor of sales, if sales are just following a trend, the best predictor of future sales is previous sales. Previous sales, that's what this is, lag values of sales. So if sales are simply following a trend and advertising has no effect, then these coefficients will be, these betas, will be statistically significant, and they're going to have most of the explanatory power on sales, the growth in sales. Advertising is just kind of coming along for the ride. You're spending advertising, but they're not necessarily causing the increase in sales. It's really just sales following a positive trend. So basically what Granger is saying, this is it. He won a Nobel Prize for this. I don't get it, but he won the Nobel Prize for this. If that's the case, if sales are just following a trend, then regress sales on past sales and on advertising, and all these coefficients, these gammas, should be statistically insignificant. That's it. That's Granger causality. So if y is following a trend, then the best predictor of current sales is past values. In this case, all those x's should be 0. So gammas are the gammas are the coefficients on x, and those should be statistically no different from 0. Does that seem like a brilliant insight to you? You won the Nobel Prize. I haven't won the Nobel Prize. I thought my side was better than that. Okay. So it really boils down to an F test of joint significance. So, yeah, we can do all that stuff. Then you run the reverse regression. So essentially what we want to see is, okay, if sales are just following a trend, then this is going to have all the explanatory power. X's will have no explanatory power. If X's do have some explanatory power, in addition to Y, then we can say, look, yes, sales are following a long-term trend. Our betas are significant. But advertising is also contributing to that growth. So our gammas should also be significant. So as hairy as that looks, it really boils down to a joint test. So we test the gammas to see if they're significant. And the null hypothesis is that X is not exerting any influence, and we have to reject that to prove that X is exerting some influence. I would not be kidding if I told you I've heard this question come up at least 5 times in job interviews for students, for people doing analytics jobs. How would you prove causality? Something like that. So even if this isn't all that clear, we're going to do it, and it's going to be pretty obvious, pretty clear. Just being able to say Granger causality is one of those cool things. But it's really a pretty simple concept. So kind of functionally doing it, let's just go with a 2-period lag model. Relatively simple. So here's sales equals beta. Alpha plus beta is 0. Beta 1, sales t minus 1, plus beta 2, sales t minus 2. Okay, so those are the betas. And if sales are just following a trend, then most of our explanatory power, our best explanation of future sales should just be past sales. That's fine. But we're also saying that here's gamma 0, and this is going to be advertising. And then gamma 1, advertising in t minus 1. And then gamma 2, advertising in t minus 2, plus our error term. It's a distributed lag model. It's finite because we've only got a 2-period lag. Notice that we have current advertising as well as lagged advertising, right? So what is Granger causality? Granger causality is, can we show that these coefficients, our null hypothesis, is that gamma 0 equals gamma 1 equals gamma 2 are all statistically insignificant. Our alternative hypothesis is that advertising has some explanatory power. Gamma 0, not equal gamma 1, not equal gamma 2, does not equal 0. At least one of those is not equal to 0. And this is an F test. It's a joint test of significance. That's it. If advertising exerts no influence, we fail to reject. These are probably going to be significant, and if it does, then if they do exert influence, then we'll reject that and conclude that, yeah, advertising actually has a positive effect. Yeah, he did win the Nobel Prize, so it's, like I said, it's one of those things where it's not uncommon to be asked. There's really only, this is the most famous measure of causality. There's another one called Sims causality, but it's a little bit more convoluted. This is the most popular one. It's also common to run the reverse regression. So now we've got x on as a dependent variable, and we're running it against lagged x's and lagged y's. And basically we're just seeing if there's some reverse causality going on, which we'll talk about later. Does this make sense?
I'm a little hung up on gamma.
Gammas are just our coefficients on advertising. I wanted to use a different notation to separate them from the betas, which are the coefficients on the lag sales. So we've got three different types of coefficients. We've got alpha, which is our intercept. We've got beta, which is our coefficients on lag sales. And then we've got gamma, which is our coefficient on advertising, lagged advertising. So this is just more messy notationally than it is anything else. We can run this regression in 10 seconds. All right. Notice that in a lot of this, there's really no, I just kind of made up a 2-period lag here. But we need to choose a lag length. We can't include an infinite number of lags. We'll lose degrees of freedom, we'll lose sample size. One way is to use an F-test approach, meaning you run a 1-period lag and you look at the F statistic. You run a 2-period lag, you look at the F statistic. You run a 3-period lag, you look at the F statistic. So you keep running these models with more and more lags, and you look at the F statistic, and with the F stat, as it gets bigger and bigger, that's better. So at some point in time, that F statistic is going to start to fall. It's going to get smaller. And when that happens, you kind of go back and say, okay, I want the F statistic that kind of maximize. I want the number of lags that maximize my F statistic. And then kind of trim back once it starts to go. This is a pretty simple method, but it usually results in bigger, more lags than are necessary. Parsimony. Smaller is always better when it comes to econometrics. Smaller models are always better. So the F-stat results in bigger models. We got these other things called information criteria. One of them is called the Bayesian or Schwartz information criteria. And it's basically this nasty looking formula that we're not going to have to calculate. But in essence, it does the opposite. What we're trying to do is find the lag length that minimizes the Bayesian information criteria. So we want our information criteria to be as small as possible. And that's good. The other is called the Akaki information criteria. And it's almost the same. If you look at these two, the log of the sum of the squared regression over t, and then plus k. And this is 2 over k. This is the log of t over t. So that's, you can see that they're pretty close to each other. When comparing these information criteria, and this is important, we'll make sure we correct this. We got to make sure all of our models have the same sample size. So remember that, well, not remember, every time we add a lag coefficient, we're losing an observation. So let's say we had, we got 30 periods, about 30 periods of data. Months, weeks, days, whatever it is. Every time we include a lagged coefficient, a lag variable, we're going to lose that period. We can't include all of the periods because we're putting the lag values in there, and we'll see it. So this is going to use 29 observations. I'm sorry, if we're using one lag, it's going to use 29 observations. If we're using two lags, we're going to use 28, and so on and so on. So that's why we need to find a way, kind of formally, find a way that helps us find the lag length, the optimal lag length. And these information criteria are often used. That's what we use. Otherwise, you see people including, notice we didn't use R squared. You'll see people just adding lags until their R squared gets maxed out at something. And that's bad. All right, assumptions, let's ignore all that stuff. Let's look at some data. We're going to look at some data on OJ.
There he is.
There's the juice. He's getting out of jail, by the way.
Yes, he is.
But we're looking at orange juice. The other juice. Specifically, we're looking at the effect of freezing days on the price of orange juice. Which is an interesting problem, that's why I liked it. Besides, I got to use a picture of OJ. So it's from Florida, and in essence, when you have a freezing day, it kills some of the oranges, the buds or whatever they are. Sometimes the oranges that are almost fully grown. And we want to measure that effect. And we know that a freezing day isn't going to affect the harvest just today, right? It's going to have lagged effects. So a freezing day today is going to affect the harvest of oranges in subsequent periods. So we're going to use a distributed lag model to kind of see what the effect of these freezing days are. So here's the price of frozen orange juice, frozen concentrated orange juice. And been growing, all that kind of good stuff. We have data on, let's ignore that stuff, freezing days. Are freezing days exogenous? Sure, it's outside of our control. You can think of it as being randomly assigned. Strictly exogenous, maybe not. But again, let's not worry about that. Let's examine the percentage change in prices. So instead of looking at prices, which is what this is, we're going to look at delta, the delta change in prices, percentage change in prices, which is basically this period minus last period. And we're going to use our information criteria to choose a lag length. All right, so determine the lag length using the information criteria. Yeah, we got all that stuff. Smaller values are better. And here is a table of information criteria. Notice the last two columns, the AIC and the BIC. Those are the Kachi and Bayesian information criteria. Remember I said that the sample size has to be the same for all of our models. So even though our 20-period lag model, and it's a lot of lags, our 20-period lag model uses the least amount of data, we have to use that sample size for all the other models also. And there's a way to specify this in data. So it's just a formality. So we have to use the sample size of the longest lagged period, which is going to be the smallest sample size. All right, and I'll show you how to do this. Then we look for the smallest one. You can see how 38, 44, 41, 37, 38, 37, 38, 39. AIC it's decreasing here again. So it keeps decreasing. BIC, the Bayesian information criteria, starts to increase after about the 19th lag. So here's the Bayesian. 52, then it goes to 47, then it goes to 37, 44, and 41. Is that right? So it's an increase. Is that right?
Yeah.
Yeah.
Yeah, see it's increasing.
Yeah, I'm sorry, that's right. So it looks like the Akaki one just keeps decreasing. The Bayesian starts to increase after about the 19th. The Bayesian tends to be the more accurate one. It'll usually pick the model with the fewest lags. So we're going to go with something around 19 lags. Remember, Bayesian information criteria, smaller value is better. We're going to construct this table. Information criteria are one of those post-regression things, so we're going to run a regression. So what do? We basically ran 20 regressions. 1 lag, 2 lags, 3 lags. We saved all those information criteria, then we constructed a table. All right, so now we've got 0 through 18 lags. 0 meaning current, and then 18 is the 18-period lag. So here are our regression coefficients. And this is again just kind of standard stuff. Notice that the only 2 significant coefficients are current freezing degree days and 1 period lag freezing degree days. After that, this one is significant, but that's it. None of the other ones are statistically significant. Now, there might be a tendency for you to want to eliminate all the insignificant lags. For example, we would eliminate lags 2 through 11, and then eliminate lags 13 through 18, right? But essentially what that would imply is that freezing days have an immediate effect, they have a 1 period lagged effect, and then for some reason, 12 periods later they have an effect, but not 11 periods, and so on and so on and so on. So normally I would advise against kind of having jumps in lags.